This is a slideshow of the jobs I've had. I'm Charles J. Michels, and this is August 2007. After I completed my Master of Science at DePaul University, I took my first job with the University of Illinois Chicago campus in the Theoretical and Applied Mechanics Department of the Engineering School under Dean Helcher. The first location was at Navy Pier at Grand Avenue in Lake Michigan. This show will last about 19 and a half minutes. The Navy Pier juts out into Lake Michigan for about a mile. The facade, the entrance, and the auditorium at the lakemost end are a standout. The rest is warehouse space on each side. Halfway in, the University of Illinois leased the warehouse and the northern edge of the pier all the way out to the auditorium, the left side of the pier as you see it in the slide. I taught there 3.5 years teaching statics, dynamics, and strength of materials. I went to night school from the pier all the way out to IIT, Illinois Institute of Technology, at 35th Street South and a few blocks west of State Street. Now the pier has changed. In 1951, we moved to Cleveland, Ohio, and I took a job with NACA at the Cleveland Airport. The lab was a small city, offices, wind tunnels, fabrication shops, test areas, library, fire and police, even rocket labs. The airplane shown is a B-58, with one engine using jet fuel and the other using liquid hydrogen. I joined the Physics Division, Instrumentation Branch, under Tom Dallas. I was assigned to Len Jaffe, who was developing a new rocket fuel flow meter. He did the electronic design and I did the mechanical design and testing. It was called an electromagnetic flow meter. By the time the first working model was complete, the research was deemed important enough to be talked about at an NACA biennial inspection. The inspection shows off our lab's best projects to aircraft manufacturers, armed forces, and other government labs. Busloads showed up every half an hour to go through 20 stops. Jaffe and I designed the display and gave each group a progress report on the flow meter. Next, I was assigned to High Energy Fuels Lab as an instrumentation specialist. Before new fuels can be chosen, they must be rigorously tested. High Energy Fuels Laboratory housed 4 large test cells and many chemistry labs. They consulted me for appropriate instrumentation to measure fuel characteristics. Instrumentation consists of transducers mounted on each rig, cabling, and recording systems. The second floor housed a control room for each cell. I'm seated in one here, and a common set of strip chart recorders switched between the cells and faster Sanborn recorders. Here Gene Corsi is shown at both of those, the Brown strip chart recorders and the Sanborn recorders. He is an instrument technologist and he helped me all through the process. In this next slide, you'll notice that there are two carts with recorders on each. These are Sanborn fast recorders for transient occurrences that are happening on the test. You'll notice that these look awfully much like the Sanborns that are used in cardiology labs for EKGs. In fact, they use the same carts, and they use much the same electronic equipment, with some exceptions that we asked to have designed for. My last job in the instrumentation branch was to last 1 year. I was appointed to be a member of an instrumentation committee to help design and build a new laboratory at Plumbrook Arsenal near Sandusky. Rocket engines are just too dangerous to be tested near a city. Our committee was to poll the project engineers of each site on that proposed new laboratory, find out and advise what they needed, and bring it back to committee for approval. And I, as liaison, would pass it to electrical and mechanical committees for incorporation in the drawings, bidding, and construction. We had GE build special data cable and mounted this on low-hanging telephone lines and brought it to Central Control Building, which also housed an instrumentation recording area. Our common budget for instrumentation was $500,000. In 1958, NASA was formed. We all went to school half days for that year, studying space, navigation, rocketry, and orbits. I noted a new organization chart at our laboratory with a new division named Electromagnetic Propulsion Division, headed up by Wolf Merkel. I wanted to see if I fit their needs. I found a Physics of Fluids article, Volume 3, page 134, 1960, entitled Coaxial Plasma Gun by John Marshall. I met with him at Los Alamos and wrote a research plan for adapting the gun to space propulsion. The Electromagnetic Propulsion Division accepted it, and I became a member and was given 3 test cells in Engine Research Building to house the experiments. The plasma is a fully ionized gas, and it's accelerated by the means of using changing magnetic fields to react on it. The coaxial plasma gun is about 20 inches long. It's 2 cylindrical tubes, one inside the other. The outer one is about 4 inches in diameter, and the inner one is about 1 inch in diameter and contains a very fast-acting gas valve to introduce a puff of gas. Once the gas is introduced, a 20 kilovolt bank is tied to the 2 electrodes, and a discharge occurs between the inner and outer electrodes, and the magnetic field in that discharge creates the driving force on the plasma. The plasma is exhausted into a glass duct, and there it is diagnosed as a single plasma shot. If successful, this would be later designed to be a many shot per second device as a continuous plasma exhaust, for instance, for a rocket engine that applies for deep space missions. While I ran experiments on the gun, I also managed a NASA contract on guns with General Dynamics in San Diego and Penn State University. I gave papers at American Physical Society meetings and AIAA meetings, that is, American Institute of Astronautics and Aeronautics, and refereed submissions for their journals and helped with some of their committees. About 5 researchers in the nation worked on coaxial plasma guns at one time. More worked on other plasma propulsion schemes. In fact, the AIAA had a special plasma propulsion committee on plasma dynamics. I was a member and I was also an officer as recording secretary. Creation and exhaust of plasma is a fast event in the gun, lasting only a few microseconds. Some measurements had to be made in the nanosecond region. The recording time for, say, 5 to 10,000 shots never totaled more than less than the time it takes to blink your eye. When I retired, my division chief said in jest at my retirement party, "If I'd have known how much time you recorded data, I would never have paid you so well." The experiment from 1960 to 68, and I gave approximately 10 major papers during that time discussing the progress on our work. We were constantly in touch with those doing the similar research in Asia and in Europe as well as in the US. In 1966, management shifted my research to another competitive plasma thruster for deep space missions. It was a high-power pulsed magnetoplasma dynamic arc system. This effort went on from 1966 to 1972. The MPD Arc Thruster is a small device, an outer electrode a few inches in diameter, a few inches long, an inner electrode a half-inch in diameter. The capacitor system to power it had to be revised. A 20 kilovolt voltage from millisecond duration is needed. A gas is flowing through the electrodes and it becomes a plasma in the arc area and then is exhausted through a magnetic nozzle. The magnet is a superconducting magnet cooled by liquid helium. These two slides show me at the initial test of this MPD Arc in the Engine Research Building. I was never allowed in an experiment area to sit next to high voltage equipment. These pictures are superpositions of me after the experiment was concluded and added to the shot picture. An electric propulsion lab building was constructed during this time and is in the west area of the lab. It consists of offices of two large vacuum tanks in the back, and then my MPD Arc experiments in a smaller tank in the lower area called Tank 8. In 1966, I started high-power MPD Arc research in the new EPL building in Tank 8 area. Tank 8 is a new vacuum chamber about 15 foot long and 5 foot in diameter, specially built for high-power MPD Arc research. The Tank 8 vacuum system consisted of 4 48 diffusion pumps as well as a liquid nitrogen jacket for added cryopumping. The pumps were located below the tank in another sub-basement. It could keep the vacuum level of space while millisecond-long gas pulses from the thruster were occurring. A new millisecond-long 20 kilovolt power system was developed to power the megawatt MPD Arc Thruster. It was a pulse-forming network designed by Steve Posta for the lab. The first Tank 8 slide shows Bob Gott, electronic technician near the pulse-forming network, myself on a fast camera viewing the discharge, and Ben Kilbrack, mechanical technician, all preparing for a test. Our recorders were housed in a special screen room not shown. The next few slides show an Asian visitor and scenes of the megawatt MPD Arc connected to the Tank 8 area. Laboratories such as Lewis Research Center require a great deal of power. In fact, when we're running our wind tunnels, we are limited to running them only at night because those plus the heavy machinery we use takes up about the same amount of power as the city of Baltimore running during the daytime. You might ask, why use capacitor banks and pulse-forming networks to power plasma thruster experiments? Well, power companies can't supply kilovolt electric power into the 10 to 100 megawatt range at short notice or in short bursts. It's impractical. So banks and PFNs are our way of getting around that. Banks and PFNs are used to store up charge, that is electricity, and then deliver it when we need it at the push of a button or a control signal. It's useful for experimental thrusters that can use power for only microseconds to milliseconds for test. In 1973, our lab began a series of RIFs, that is, governmentees for reductions in force or layoffs. We weren't laid off as yet, but our research was reduced on long-term flight projects such as plasma thrusters. I was asked to apply plasma knowledge to developing a new laser media. I had built a Bloomline-powered fast discharge apparatus to use as a test bed for plasma laser media. Don Chubb, one of our lab members, had estimated that a xenon discharge with calcium doping would laze in a charge exchange mode. After a year of testing with him, the experiment did not show the calcium xenon discharge would laze. The lasing tests required using monochromators and tunable dye lasers to probe the discharge. By the time we built the fast discharge Bloomline apparatus, Sheldon Beasley, a new electronic technician, was working at Tank 8. Here he's shown working on the fast discharge Bloom apparatus with a monochromator measuring the spectra that emanated from the fast discharge. I've been lucky to have such a career. What ingredients might I've had luck with? First, I had parents, my father especially, who were good teachers. And when I was a young child, they would always explain things in great deal to me, even when we went on little short vacation trips or on excursions in a streetcar. Secondly, my training had good teachers, and I enjoyed science subjects and took a liking to what I saw in physics. Thirdly, I had the opportunity to study radar in the Navy, and that gave me a great training for what I needed. And lastly, the opportunity of working at a government laboratory was tremendous, especially in the heyday of space. Money was no problem. I had all I could ask for with extremely good support help, technicians, engineers, and all the backup of every service in the laboratory.